Okay, Dr. Mbatha,
Okay.
thank you very much for joining us again this afternoon. This is the last lecture of the series on Earth systems and climate change modeling and Python for geosciences. And the last lecture in this module will be delivered like the previous one by Dr. Mbatha, who is based at not at DUT, at UNIZUL, at University of Zululand. Yeah. So Dr. Mbatha, we are really very happy that you're back with us this afternoon, and so are all our participants. So you're most and welcome to share your screen and start your presentation. And sorry, and just for another organizational issue, I have unfortunately a meeting that I have to attend at 3, but I asked my colleague, Professor Sinaisky, he will join us 2:45, and he will make sure that everything is on track and will help you with the questions when I have to leave. Yeah, thank you very much. Oh, but now you muted your famous microphone.
Oh, okay, no problem. I just shifted internet because I think my wireless is not good.
Okay, we will find out.
So that's fine. I'm just switching very quickly from the Ubuntu computer to this Windows. Just 2 seconds.
Yeah, no problem.
And then
take your time.
Today's lecture, I thought of 2 things. One is to quickly go through a notebook of NO2 seen by a satellite
Nice.
over South Africa. And also my target was really to look at Durban looting in terms of NO2. And then I want to quickly,
excellent.
Yeah, and then I want to quickly run to my deep learning notebook, which I designed to do modeling of any time series, which we apply on COVID data. But what we do is we pre-process the time series before we feed into the deep learning LSTM. I think that was relevant for this class because of the modeling class that happened before this.
Yes.
And then there's a bit of wavelet in it, of course. My interest was to talk more about wavelet, but at least, you know, if I talk about this, it's fine. The wavelet class is also there, but if I can also give it if I have time. So my class will be, so I need to move. I'm very sorry. I thought this computer will hack, so I had to fetch my Windows computer very quickly. What I need from here is just this code. And then I can just project it here. And thank you very much for everyone for attending this class. Okay, so that should be fine now. What I'll do is I'll just throw these 2 notebooks here. They should not have a problem to open so that I can share and we can just show what we can do. So maybe I'll just say, cool, and then we can share. Okay. So can I share now?
You're welcome to share. Yeah, I think everybody's ready.
Okay, so so I'm sharing my screen. I just want to run these 2 notebooks.
Yeah. And we can see your screen. We can see your screen.
Yeah, so I just start afresh my Anaconda prompt, and then we just call Jupyter. Okay. We'll open it using Jupyter Lab. Okay, just a few seconds of opening my Jupyter Lab.
You know that we know how it works.
Yes, yes. We should jump into this.
Yeah, there's some action now.
Okay. So now that's here.
Perfect. Now we can see it.
Now you can see my screen. Okay. I'm going to go here and go to school. I just quickly through it here, so these are not relevant for this. So I'll just close them. Then I will start with this one.
Excellent. Perfect.
Yeah. So we can start talking. And so what happened is that initially I had not used this data before in Python. I have one journal that I wrote with some guys who are doing atmospheric chemistry, where I did this using JavaScript code editor. So after the class that we had some 2 days ago, I thought maybe let me come here, start this notebook very quickly, come back and present this to you so that you can see what else you can do quickly using this X-array. So okay, maybe let me. Yeah. So first of all, in my notebook, well, I'm using Sentinel P5, which is a satellite, a very high resolution satellite, European satellite. It's Copernicus. And I knew about the satellite maybe 2 years ago, where we were looking at some of the satellites that could detect geophysics and so on, and to find that this satellite is a very highest resolution satellite you can find that can give you chemistry and so on. So I grew interest in it, and then hence I started to do some small Python codes to read data. So what I did here is initially I wanted to look at the looting that happened at KZN. Of course, my script is going on because this is like 2 days ago, and already I find some interesting stuff. And then I also noticed that I need CHPC to process some of the stuff, especially if I want to create that video that will look at the pollution, how it changes over time after the looting. I'm sure you know about the looting that happened. I call it a Zuma looting. I was here also in KwaZulu-Natal when these people started smashing things and breaking things and banning factories and banning some things because of some politics and stuff like that, and so on, and some many other reasons that they stayed and so on. So I thought that when you were sitting here in Richards Bay and you look around, or when I could not drive to Durban from here, so when you look at Durban, there was smoke everywhere and so on, and people were burning, and there's a lot of pollution. So I thought, okay, like let me look at whether this high resolution satellite could look at that, but you end up seeing other very interesting things as well in the project. So this was inspired by that. So you would remember how you can load some of the packages that you need. One package that I would need to run, especially now that I would need some assistance with the CHPC or some supercomputer, is this hub function, which helps you modify different data so that it is in equal grid for you to be able to compare or to use it together or something like that, because the way this satellite orbits and the way the satellite calculates data in different places is different. However, because of those computational abilities, the period was too short for me to also run this on on the CHP system. I think you can do presentation mode. Yeah. So these are the functions that you load. This time I use try because there are just too many of these modules that I must load for me to do this. And I just make this small loop system, which is a try system, so that when I have one or two of these modules that I could not load properly, or maybe I forgot to install, then it can give me this nice message here, or it can print that everything is fine, and so on and so on. So what I need, again, like last time, I need Catopy, I need your CM Ocean, and I need your Matplotlib as usual. And this term color I use here, for instance, this is the first part where I use it. I want to make this line green if all my packages were able to install properly. So I use NumPy, all these normal ones that I would use, but there are some additional ones like harp and so on, which I explain why I use them, because apparently there's a lot to do in the data. If you want to manipulate, for instance, dictionaries, this is the one that you use, for instance, and so on. Within the process, I quickly learned also different functions that you could use when you are dealing with this gridded data and so on. And it was really very interesting. So these are all the modules that I import and so on. And this is my method, how I import it. I did this way because I don't want to get that large message of an error every time when you have a module that could not install properly. So for instance, last time I installed it, this message was able to sit here, which means everything was installed properly. If I can run it now, it will not, of course, because remember, I do this in a Python computer, so I'm ready to jump into the CHPC computer. So I just took this code and put it here so that I can talk to you guys. Okay, so this is the styles. You remember this, the plotting styles that I spoke about last time, where it will give you a very nice plot, which is like formatted properly so that you can use for applications. Again, to remind you, this was initially targeted for Zuma looting, but of course, I will show you where I need the CHPC system to sort of at the end give you a very nice video of how the pollution changed from before the burning started or the looting started to during the looting and after the looting. However, there's more interesting stuff that you can see. This is just to quickly look at what how you use your XRA to read your NITheP file and what exactly you want to access. You want to access your global attributes, your metadata, and your product group. And where I saved my data is actually, I made a folder where I have the Sentinel P5 in this, in my Linux computer here. And the data, I saved it under looting. The data that I used, I downloaded it from the same website that I showed in the previous class, that Geodisk website. So if you would go to Google, for instance, you go to NASA disk, Copernicus guys do work with NASA. So this data you can also find inside the NASA disk website. Okay, so in the meantime, when it is trying to open, so this is how I read my data. I just, of course, you know, I want to read a series of this data. So this is the path where it is, and then this is the files that I want to read. And then here I'm just sorting those files really so that, you know, they are sorted inside this path. And then here I'm just displaying them. And this is just my message that will tell me, printed in blue, that will tell me how many of these files are there. Let me tell you, in normal basis per month, I will get about, I noticed that you can get about 68 of these files. I will tell you why, because in the process you learn about how the satellite orbit and so on, so on, how it how frequent does it visit your area of interest. So some of these sweeps of the satellite can pass over each other as it shifts just a bit. So you can end up having 2 sweeps of the satellite per day, hence you can have more data files. So sometimes you will not have data files. So already this data, before I ran, I quickly noticed when I downloaded this data that you should first, for instance, Sentinel 5P. So you can just write the keywords Sentinel P5 there just to show you. So this data is already here. So you can get, so you can notice that, you know, these sweeps, if for each sweep of the satellite, for instance, you can have, it will shift maybe just by some kilometers, this direction or this direction. So it will end up getting 2 sweeps per overpass of the satellite. So that's what we can quickly notice. This is actually a very good example. And what I learned a lot about this data is that, you know, it takes much more wider pictures of the northern hemisphere. Of course, it's a Copernicus satellite, and hence sometimes it misses us here in South Africa. Maybe it will miss South Africa by just a few kilometers or something like that. So that's what happened. So you can just download this data. From this data, you can get a lot of parameters. You can get NO2, you can get SO2, you can get aerosol index, you can get some net parameters that you can use, very high resolution net parameters that you can use as an input to whatever model we are using, for instance, WAF and other models that we are using. What I'm sure about is that currently there's no one using that, and I'm sure it would be nice to test some of the things you get. So for instance, you get cloud information that can be a very good input in a model. You can get other things that are really useful for weather and climate modeling. So quickly, I can quickly identify how many of these files I have, and then I can just, what I did before I come and do the analysis of the whole time series, I quickly check which files are good for my analysis, because I need to select the grid over the Durban, for instance, and maybe include a bit of Richards Bay and go inside that way to Pietermaritzburg, the other city just north of Durban, and so on, where there was also banning during this looting activity that I was doing. So I was going to each and every file. So I had about 60 something files. I just want to look at them if they all were able to pass over my region of interest. So I'll show you how I did that. But first I would print out the file here. So I go to each file. For instance, I was looking at file number 24 here. Remember, Python starts from 0. So this is file number 24. So it will be like your day number. It will be like your day number. So it will be like your 22nd. It means here I already filtered some of the early days which could not pass over my origin of interest and stuff like that. So here I'll just look at each and every file and look at what exactly is its location, because what I had done is to, when grabbing this data, what I did is to go to the data itself and only pick those data points that are over Durban. So for instance, you would filter define your region here. So what I did is to say I want anything that passes over, for instance, South Africa, so that I don't download this file again. So I just grab something like this. You can do, wherever you are, you can also do the same. So it means, what is a drawback about this method when we're using this satellite is that it will not only take data that passed here, but it will take those sweeps. So it takes the whole thing, but as long as that thing touch this box. So it means you need to do a bit of computation when we're now calculating whatever you want to calculate at the end. So I'll give you an example very soon. Here, remember your your X-ray assists you read attributes. It also assists you read your metadata and the actual product and so on. So here, this is just my way of looking at different things that are being read by my X-ray. For instance, here, this is another way of saying this is equal to, I'm reading multiple files. So just, okay, for a start, I was just reading one file, this file that I read from top here. I just wanted to open it and look at these properties like your attributes, the metadata, and also product. So I read that data as if a Sentinel-5 image global attribute, and I also can read it as metadata and so on. So then it will display the information about the time series, the data for me. And here I'm just printing out what exactly is it that I'm reading. And so when I print it out, you can see these are attributes. It will tell you all the information about the file itself, or the measurement, and so on. It's a Sentinel-5 precursor. All sort of information is for what day and so on and so on. When was it last processed, and when was it modified? And then for metadata, it will show you the information about granules, information about the latitude, your time, and all those things. And the actual product group, that's where you will see information about the measurement and coordinates and so all sort of information, what is being measured. For instance, in this file that I downloaded, it's for nitrogen dioxide. Of course, you can see something different also if you download sulfur dioxide, because there was burning there was this type of exchange. I'm sure after this, it would be nice to get someone who is interested to sort of look at nitrogen dioxide and so on. And so on. So these are the parameters that are there, which are under your product group. Okay, so well here, because I wanted to plot, or maybe just later look at this one single file that I took. The 22nd is few days after the looting stopped, because they say, but I can't remember if the looting stopped on the 19th or 18th. I think it continued a bit and so on, and burning still continuing in some of the factories and stuff like that. So when they talk about this looting, they say it started on the 9th or 8th, and it ended on the 18th or 19th, but I think it went further than that. So this is when I just wanted to look at the time select the time for time reference. So it means it is the time that this file was taken. You can see it's 2021-07, 22nd. So it's because I wanted to use it later, for instance, when plotting. Okay, so here you can look at the dimensions, so you can select your actual data. So for instance, if I have this data, just one single data, that file, because there are very many of these files, there are files for all the days, sometimes 2 files per day because of the overpass. So I select from my Sentinel-5P image product, I just wanted to select the tropospheric column of nitrogen dioxide. Tropospheric column because I don't want to go higher than that. I don't want to go to stratosphere, which is like you're above 15 kilometers. I want to go closer to the surface. So tropospheric data is the better choice if you want to look at pollution and so on, because we've noticed that here there's also some stratospheric data and so on and so on. So, and then I just can take this data, and then I just want to look at its dimensions. So these are its dimensions. So it varies both with time, latitude, and longitude. But I can also print out coordinates and to check what coordinates are there, and information about attributes as well, so that you can see what sort of parameters are there. There's also a vertical column of nitrogen dioxide in the data in the file. There's also this one, and there's also some other parameters. The data is measured in mole per meter squared, and I need to convert it, and this is a factor that I need to multiply with for me to convert this data into mole per square centimeter. With moles per square centimeter is one unit that is normally used by atmospheric chemists when they are doing this type of measurements. Okay, so I can quickly look at this file, of course. So this is when I was, so I go to NO2 and just take this multiplication factor, which is this. I just noted it here. It's here, and then I just take it and multiply my data, my NO2 with it, and then have a quick plot. So this is just a normal matplotlib plot. I defined that my x is latitude, sorry, my x is longitude, my y is latitude, and I just use this type of color map, R, and then I define my maximum and minimum of the color bar. You will see this is the one sweep, remember, and when I ran this line here, it was for the purpose of using in my plot where I used it so that I plotted here. So you can see this is a sweep, and already I can see that as it goes up, I think here it's around the equator already. You can see that when it passes over Congo, you have this pollution that is happening here in northern Angola and the Congo region because of the biomass burning and some activities that are happening in the forest there and so on and so. But this is not well and nice because, you know, there's no map. So I'm just looking at your latitude and longitude position and thinking, okay, around the equator, it's that and this. What I can do is I can just use ChPy to fit in the map here, but it already looks nice. Remember, I'm using that scientific plotting style, and you can see it is ready to be used, but of course I need to develop this more. So what I'm doing now is to project it over orthographic projection, and I just put in center over South Africa. This is like your center of South Africa here, just so that I can be able to zoom into South Africa and look at what is happening over South Africa. So I thereafter take my data. Remember, this data is this data that I read here that I converted into a mole per square centimeter, and then I just take that and I plot it using P color map, and then do the same thing. And my longitude is X direction, latitude is Y direction, and I choose a color bar, and I still use this plotting option, and then and then I just add these features. These features you can get them from this. From ChPy here, as you can see. So ChPy has these features that I'm selecting right now, where you can put in even some boundaries, political boundaries, and so on and so on. So I'm putting coastlines. I'm taking it from ChPy. And then I'm also putting borders. This is how much I want them to be bold and so on. If I say 0.5, they will be a bit. They will not be that bold. But this is one is a bit bold. And for instance, if you look at line style, so this one will be dashed, and then I just want to put the title as well. You use a little bit of LaTeX because remember NO2 is NO2 with the subscript, and then here I'm saying Q value is equal to 0 because I have not flagged any data. So here I'm just using the data that I'm reading as it is, but I note that when you take measurements using a satellite, there are many other calculation errors that may happen. Hence, each and every data will come with a flag. For instance, if there are clouds, if there is this, if there is that, they need to consider that when taking the measurement. So this flag thing is not done in this plot. So I'm plotting this in a global map So if I deactivate this, it will maybe zoom into the area that I want to do. But if I activate it, then it will give me a big picture. So now, after putting all these extents, the title, the grid lines, and then here I'm just locating the cities, the three big cities here in South Africa, Durban, Johannesburg, and Cape Town. These are latitude and longitudinal positions of them. And then I just put the marker size and also project them using green curry maybe or something like that. So these are the cities, and I told you that that pollution we saw there was over Congo and so on. And you can already see that we are seeing South Africa here. There's a bit of pollution there. Durban is a bit of pollution, but there's a lot of pollution in Johannesburg around there. And when I say each sweep sometimes can miss you, you notice if you're around Limpopo here in somewhere in Venda, it will this sweep has missed you, so you will not get information about you. Or if you're around Nelspruit or somewhere there, then Kruger National Park is not getting any information about you. You probably need to shift to another one. But if you go all the way to West Africa, Cameroon, and so on to Nigeria, it has detected your activities there. But what is interesting is that you can already see that there's a lot of NO2 values around here at very high resolution and so on. Well, what I know is when it comes to NO2 and Sentinel P5, these areas are not studied. NO2 has been used mostly in the Northern Hemisphere, and we have one study that we did with the postdoc from SANSA, where we looked at NO2 over South Africa as well. So there's a lot of things that needs to be done. For instance, if you want to do these type of studies, or in Congo here, there was a volcano that happened, and it injected a lot of SO2, I'm sure, a lot of CO2 and all those things into the atmosphere. So if you want to look at this, then you can go to Sentinel P5 and look at the dispersion as well using some dispersion models like FlexPart. I will talk about FlexPart now. So this is how each sweep would look like and stuff like that. I don't know whether I'm talking too fast or whether I should give one opportunity for a question before I continue again.
Dr. Mbatha, we always encourage people to ask questions. So everybody is welcome to raise their hand or to use the chat and or just switch on the mic and ask. At the moment, I don't see any questions, but the participant should ask questions because there is a book prize to be given.
Okay, no problem. So maybe I should stop just a few seconds to give an opportunity for a question or two. Okay, maybe I will continue there. Okay, so that's what is happening. So this is how powerful then is X-ray and Catopy and some of the modules that I installed here. Even myself, I'm really impressed by what this can do. As long as you really know what you're doing, you do something very, very nice. Well, I can tell you a nice story also that I've looked at recently. I looked at ozone also from Sentinel P5 in the stratosphere. There's an ozone hole that sits over here. So I looked at that ozone and it looks very, very, very nice and stuff. And I think it's the first time that at high resolution, you can be able to monitor the ozone hole and so on. So the ozone hole has an implication because, you know, when you have that hole, then you start to have UVB radiation from the sun passing all the way to the surface of the earth. For instance, people who live around southern Argentina here will suffer because of your UVB radiation, which is, I think, about 200 nanometer or something like that. So that's that. And then that's all about looking at a single file. But again, what I spoke about here is that this is not filtered. So this data is not filtered. I did not do anything to this data. You know, it is just me and a computer and the one single file, and I'm trying to look at what is inside with the computer helping me look at it. But I know now that I must perform some small computation so that I flag out the information that could be because of different reasons. For instance, some clouds or some calculation error and so on could create some of the false information that can be given by satellite. For instance, surface albedo, or sometimes the presence of no activities such as saturation, of course, assumption about clouds and all those things. And even geometry can give you some calculations that are bringing in errors. So, and then the quality flag of this data ranges from 0 to 1. So if you take about 75% of that data above 75%, meaning anything that is less than 75%, then you are at very high quality of the satellite itself. So that is done for each and every pixel, and the resolution of the satellite is 3 kilometers by 7 kilometers, I think. Recheck again on that information. But you can change the flagging to whatever you want, because sometimes, you may remove some of the information that can be useful for your analysis. But those who are doing modeling, for instance, or those who are doing comparative studies, and those who want to use this data for input, I noticed that they use 0.5 as their flag. So they take anything above 0.5 50% of it. Because it will mean anything less than that, they consider as data that is supposed to be flagged, which is supposed to be filtered out from the image itself. So here I just do my first filtering also. So this is the name of the image that I read. Just to remind you again, this is this image that I read here. You can see it is here. It already is multiplied by this value. So it means it is in mole per cubic centimeter. So when you go to that data and filter out, so inside, if you are using X-arrays, it's not like using NITheP. It has its own functions. For instance, if I take that X-array image and then just say where this image, the product image Q value is greater than 0.75, it means I just want to drop anything that is less than 0.75. It means I'll be left with the information that is above 0.75. So it is just one line. I remember when you are trying to filter, when you are using NITheP, you probably must write a loop that will take a few seconds, few minutes to run or something like that. I've not done it using X-array. NITheP, maybe I did it some time ago. But of course, if you want to use 50% also here, you can just put in 0.5 and see what that does to your data. So that's what I did. And then I again project that filtered image. So now this means it's my filtered image now. Project that back to my image for visualization. The projection I'm using is orthographic. So I'm putting orthographic as a base, and then overlaying my data, plotting it using p-color map. So I also again put in these different parameters that I put up there, and then thereafter list all my features. But what I want to do a subplot. It means I want to do two plots. One is to plot the flag. So I'm just using the Q value, plotting the Q value here. And then two, I want to plot that data, which is filtered. So side by side. So here I'll plot the data, the Q value data, and here I'll plot the data that is filtered, and all these other things are normal setting up of my image, your political boundaries, your land, your ocean, your rivers, and all those things, and title, and all those small things. So when you do that, you can also save your image, of course. I was using this PC here, so it will save it to some folder. You can even give it some bit of quality on your image and so on. So this is how it looks like when you plot, when you remove some flags. it makes sense that these flags are less than 0.75. You can see it was removed here. All those patches were removed here. It's because this equator area here, there's, of course, it's a low pressure region. So there's always clouds there. So, you know, so those clouds will probably be there and you'll have to filter out, so you can't see the chemistry below those clouds. And so, or those clouds are giving you false information and stuff like that. And then, but you can see a lot of pollution over Congo and northern Angola. Of course, we know why there's a lot of pollution around Congo and stuff like that. And interestingly, you can also see a lot of pollution here in South Africa. Actually, we have stronger pollution than any other place in the southern hemisphere when it comes to NO2, SO2, and all those things, because of the mining activities that we do around Mpumalanga and stuff like that, and Gauteng, and so on. So these flags help in that way. So you notice that these bluish areas here are above 75. So we were able to capture that data, but these ones which are less than 75 were left out. For instance, these areas here, there's a lot of ice here, which gives a lot of false information, but that was removed and stuff like that. Okay. And then the other thing is to subset your data. You probably want to subset your data so that you can zoom into wherever you are. For instance, this allows you to look at any place you want to look at. For instance, if you are in Congo, you know your latitude and longitude, you can pick on Congo. If you are in Algeria or wherever, Burkina Faso, or maybe if you are in Guinea, if a satellite was able to pass over you, I have a very nice friend there in Guinea who is doing atmospheric physics. I'm sure he would like to use some of this. So you need to define your coordinates where you want to cut your data. The easy way is to define your upper right corner and your lower left corner of your grid. So meaning the portion that you want to zoom into. So here, that's what I did. And what I did is I filter it. I filter my data. As you can see, I'm also using where here. I'm just looking at going to the filtered data, take the latitude that is less than my my upper right corner, and so this is like creating the grid, cutting the data on a box, really, and so on. So I want to take data that is between this and this area and this area, and also this latitude and this latitude, which will create my box. And then I take all that, I project it over my map again. Well, so here I just want to go down to softer boundaries, because remember now I'm inside South Africa, so I want to see provinces and other small things. That's why I'm using this data now here. So, and then I just subset my data, put my subsetted data on a color P map, and again use the same settings that I was using all the way up, and it will now take my data over South Africa. Well, what is interesting about this that I've done here is that I can easily see places where there is activities that are raising pollution. In normal places, when we have a satellite that is not high resolution, there will be just a red spot here. But with this high resolution, I can see that in your Standerton area, there is certain pollution that is coming. When you go to Secunda, somewhere there is a lot of pollution that is coming. When you go to Emalahleni, where there's coal-fired power stations, this thing gives you exactly the location, and it directs you right on top of it. I had never seen such a thing that you can see exactly where that pollution comes. So you can see also there's a hot spot over Durban and stuff like that. It spreads a bit to Pietermaritzburg. This area is always a culprit south of Johannesburg, this area here, so you can see also. Well, what has happened also during this nice small demonstration of X-ray that I decided to take up is that I noticed that, you know, there seem to be some blowing of this air towards this direction here, which means this comes at the right time, because now that we are working with CHPC, initially we were unable to run FlexPart. There's what is called FlexPart, where you can actually use fluid dynamics. It's a Lagrangian model that uses fluid dynamics that can help you track the motion of this pollution, so that you can also backtrack and see exactly the source and see where it spreads to. Maybe some of you are asking, what is this? Remember, they built a power station here called Modupi, so you already have the pollution that is happening there. So this X-ray and Catopy thing gives you this nice image. Even your output of the model, you can easily project it over a map and do whatever you like, a very nice projection. So let me stop a bit again and ask if there is a question or something like that.
I don't see any raised hands, and there is nothing in the chat.
Okay.
But,
okay, maybe then let's continue. Maybe people
please,
will ask
participants, get a little bit more engaged with the speaker. give him some feedback. Yeah. Thank you.
Okay. Okay, so that's that. And then the part where we need CHPC now is when we pre-process this data, because this is just one file, but you want several days of data. So, and already you can see that this file is filtered. Some of the areas are not there because each and every different sweep of the satellite will have its own problems. You will filter it differently. So you probably need to recalculate this using HAP, this HAP that I'm talking about, which needs a bit of computational power. So that each image can be in a same graded form, so that you can do averaging, you can do time series analysis of these, and you can even do movies, a movie of pollution for every day. So here, that's the step that I'm doing right now, where I'm zooming in further to the point where I want to look at the pollution. So meaning I'm just zooming at this, I'm zooming here, because of course, you know, when I use these areas, I already know there are problems there, but I just want to see pollution around this area here. And when I zoom into this area, I want to take several files, which I must recalculate to level 3 data, because this is level 2 data, by the way. So, well, when you want to do something meaningful, you probably need to go to level 3. When I go through some of the activities that you need to do on this satellite, this is to upgrade the level to level 3 through pushing this data to all these data files to what is called HAP. And then HAP will assist me to reproject the data and make these same latitude and longitude. So I need to zoom a bit further into Durban and Maritzburg and the area which we had looting. And then, well, I need to look at this hub needs me to define the grid and pixel that I want to use when recalculating. In this case, I want to take maybe my lower left corner latitude so that it increases by this much towards the left, for instance, towards the right, for instance, and maybe also it increases by this much towards the lower latitude and stuff like that, and so on and so on. So that's what I'm doing here. I'm getting how much the length, how much the increase of the grid should be, starting from my lower left corner, for instance, and so on, so that I can have a grid that is on top of my area, and that grid that I sort of create will be the grid that I push into hub. So hub is this nice routine here, which needs a bit of CHPC, where you select the data and tell the computer that you want to filter it by 75. You want to also derive your tropospheric NO2 number density data, which is, by the way, already converted which will be converted into mole per cubic centimeter. We want to also derive your stop time of each file. So, and then you also want to, give it a grid. So these grids that I'm talking about, that I'm calculating here, are applied here, so that you sort of cut this grid, and then in this grid, you bin it by these steps that you mentioned here. So use those steps, and then it will go so many times towards the higher latitude, for instance, or it will go so many times towards the higher longitude and stuff like that. So that it is binned. So this is the part that I noticed that, okay, I get stuck because, it needs a bit of computer, and then you can keep some of the parameters that you need. For instance, you will notice that I'm keeping this one, I'm keeping this one. Maybe later you want to look at the tropospheric column, or you want to look at stratospheric column, or you want to look at the absorbing aerosol index. These absorbing aerosol index are very important. Actually, they can tell you more about pollution during burning, probably more than NO2, according to what I think of, because when you were in Durban, you will notice that it was dark. So the sky was full of pollution, which would mean this would sort of maybe detect more pollution than maybe NO2 because of the burning. So this is the step I need to run, which takes a long to run, which means I must run only a few files and try to recalculate them and so on and so on. And these are the steps. This is one step that I must go through to convert my time into the time frame that is understandable for me to apply recently towards the end and so on. And then this is when I reprocess my time then and so on. And then this is when I take all the data that I have ran through this and stack them, read them using open multiple files using X-array, and then I nest them also because now there are many files, and then I concatenate them using time. That's why it is important for me to make sure that the time is understandable by Python by applying this process function that I did here. And then I use Chunk because I'm using Dust, so that at least my computer is a bit working better. So after that, then I will just, I tested this. Of course, you need to get data before looting and data after looting and stuff like that. It's a pity I can't run this now. Of course, it will take long. I can't run even a small thing because now it's I'm using this computer. I'm not using my Linux computer. Yeah, so and then you can choose the data, for instance, you can slice the data. Remember, using X-array, you can just select the data. That's what is nice about the X-array. You can just go to time, slice. Remember, looting starting on the 9th, so you can just take a few days, or you can just take time before or during the looting. Looting started on the 9th all the way to the 19th or 18th. And these are the days after the dates where there is looting. Well, I can tell you that, okay, there's a very strong pollution over Durban that I see, but of course, this will need to be recalculated properly because I need to rerun this inside CHPC. I heard that you can run these notebooks inside CHPC. That's what I need to do so that it is easier for me. But already you can see there is a bit high pollution. So my hope was that I would run my Linux computer so that I change days physically so that you see that during pollution, You'll see some areas where there were fire, you'll see some patches of pollution that was happening there. And then when you go to what happened is that few days after looting, there was a strong plume that was sitting around here, which seemed to be pushed towards the ocean. So that was interesting about what I see. But what will be nice is to have a nice video stacking and doing all these processes and stuff like that. So what I'll need is to run this script inside the CHPC system. Okay, maybe let's stop here with this and make sure that before our time ends, we touch on the deep learning time series forecasting notebook. Okay, I'll stop sharing a bit so that I see who is here. Maybe some people can talk to me. Any questions, maybe?
Yes, Eric, you can ask a question.
Yes, thank you, Dr. Mbatha. I've got a number of questions regarding what you were presented to us. That's a lot of information and very interesting. So my first question is the pictures that you showed us. There's a bit of pollution in the Congo area, and there's a bit of pollution. I mean, you explained that because there's a lot of mining activity happening there, because that was NO2A. But I noticed that there's also a bit of activity around Cape Town. Is there a reason for that, or is someone did you try to explain why there's something around Cape Town? That was my first question. The second question is you were talking about NO2 mostly, but at the end of the day, is it about NO2 only? How about CO2? How about SO2, SO3? I think I don't know whether SO3 can stay in the atmosphere for a long time. I think it decomposes, but SO2, I think. Is there that? Can you download files that probably combine all those so that someone can get an aggregate of all the pollution that might happen in the atmosphere? Then my last question is, you mentioned something about taking your files to level 3. I didn't really get what that means. I mean, from level 1 to level 3. Probably if you can just quickly go over that.
Okay. Okay, thank you very much. Yeah, that is very nice questions that you're asking. Well, first of all, you know, Cape Town is a city. NO2 comes a lot from cars and all those things. Cape Town is a very big city, so you expect pollution there. So it is always there too. So that's why you have pollution around Durban as well. All the places where you have a lot of cars and so on, you will get high NO2 values. And then when we talk about NO2 for this study, this was to demonstrate how one can use X-ray and cartography to sort of view atmospheric chemistry. Because I didn't want to talk about rainfall and all the other things that would normally be expected by maybe a person who is doing applied climatology. But all this is related. But well, then let me tell you something. I did not only look at NO2, but I do look at SO2 as well. Okay, yeah. Whilst we are talking, maybe I just have a quick Google here of this work. So, well, that's why I talk about the aerosol index as well as one of the indexes that can show you details about pollution and stuff like that. But the parameters that are inside Sentinel P5 are NO2, CO, ozone, methane, you have SO2, the aerosol index and so on. They don't have all of them, but once we have NO2 and SO2, then it's even better. I can tell you that if you go to those areas with coal power stations, you will get a lot of SO2. And then what was the last question? or the level 3. Okay, you'll notice that when I opened this file, it was on, so level 1 data is near real-time type of data. It is near real-time. So this satellite is powerful because it can give you a near real-time type of data. When do I use this near real-time type of data, for instance, myself in JavaScript, even though I don't really want to use much of the JavaScript thing now. I use it when I look at the companies that are here in Richards Bay, because from time to time there are leaks. So the data is few days delayed. So I just grab on top of the company, like for instance, Fourscore or Mondi, and then look at the time series, because we don't have sensors here. We don't have sensors that will give you this detail, for instance, that you can put everywhere and stuff like that. So when I say level 2 is the format of the data that you will get when you download it. And then you will notice that when I say I move to level 3, I say I move to level 3 because you will notice that I filter my data, for instance, first of all. I filter my data by 75%. And then I go, because I want to read all the files at the same time, I apply this module that is called Hub that will read the data so that it is in the same format to be used together. That's what this level 3 is about. But you can also get this information from the website, their website, the guys from Topomi. And then just to talk more about this Topomi, I wrote this. So this is a geoinformatics paper. It was for the first time I have a paper in applied geoinformatics, and Lerato was doing a postdoc with me, some of the activities here from SANSA. And then what I did in that paper, we did not look at NO2 only, but we looked at SO2 as well. But we didn't use Topomi only, but we used other satellites. As you can see, this is SO2, this is SO4, and we get a lot of that and stuff like that over this area here. We ran wind as well. At this time, we did not have the capability to run FlexPath model, which is much more advanced than calculating wind quivers from U and V of the fluid dynamics, so that we can see the direction of wind and also try to explain the inversion or something like that. So this paper was basically about that, and I think this is the only paper that explains the use of Topomi to look at these parameters. So far, we also use the ground-based sensor data that is there and stuff like that in different areas where there's this high pollution. So we didn't use NO2 on. So in this study, it is the first time that I capture all this inside Python, and I think it works better. Here, this was level 2 data, and the quality of what we see here is now better because we now also move this data to level 3. We also filter it by 75% or 50%, but 50% probably will not be good for the quality of what we want to see. Something like that. I hope that answers you, Eric.
It does. Thank you so much.
Okay, sure.
Quite interesting information.
Yeah. Okay. Okay, so is that fine? So we can jump into our other notebook. The other notebook.
So, yes. Yeah, I think so. Yes, we should
not have a lot of time to look at this notebook. I think I closed this. I think I closed my. Okay, so let's quickly jump into this so that I demonstrate quickly what we are doing here, so that I'm sure you'll be happy to know that here in the University of Zululand, we are also doing this type of work. I am a person who did a bit of atmospheric physics, space physics, but I'm taking that now to other things. For instance, decomposing energy of physical data, really, or looking at periodicities of energy of physical data. So, and then by having LSTMs, for instance, I have written a small module here, a package that I was hoping to show you here, different functions that I use in this notebook here that assist me calculate or perform LSTM for time series forecasting. But what I do is I decompose the time series before I feed the data into the LSTM. So the model looks like this. So we are writing, we were hoping to present this actually in the machine learning conference that was hosted by UKZN, and I don't know what happened today. So we have a nice paper that we are writing in Overleaf, myself and my PhD students from mathematics department, where we are trying, we have successfully used 2 or 3 different decomposition methods so this is LSTM to decompose the data before you push it into an LSTM to create a hybrid LSTM. So this is relevant because a few days ago you were doing models. So what we have done is you give me your time series, and if I was new to LSTM, I'll just take the time series and push it into an LSTM, maybe divide the time series into 70% and 30%, use the 70% for training and the other percentage for testing the data, forecast, and so on. But what we have done with my student, some 2 years ago, I did a hybrid model that uses EMD and empirical wavelet transform, meaning you are decomposing with 2 methods and you compare how these 2 methods perform. So when my PhD student from mathematics department joined me, I suggested that we use several methods of decomposition and see if we create these hybrid models to forecast time series, how these decomposition methods work if you decompose each and every IMF and so on, because this is a long-term, short-term neural network, then it should be able to capture short-term variability and long-term variability, and you sum them at the end. What is happening is that we now have this system where we push in the time series into IMF. So where we decompose the time series into different IMFs and push it into an LSTM before we do forecasting. Here we also do 70-30 or something else, like 80-20 separation of the time series, so that we use the other portion for testing our time series, and then we can forecast. The idea here is to forecast anything, including the ends of signal, all the type of things that are there, so that in few day time I can forecast and tell you that, okay, in the next few months, this is how it will be. So the idea here was to apply that on the COVID data that we have, the COVID data, new cases. You can also use any of the information that you get from COVID data. We are doing that in 3 countries. We are doing that in Egypt, South Africa, and Zambia. And we randomly chose those countries, but also we're controlled by the quality of data from other countries. So the models depend on these decomposition methods, and also they depend on denoising. We denoise sometimes and push into this decomposition method. So this is the structure of the models that we created, and these are the names of the models that we created. So this code here is for that purpose. So we have confirmed cases of COVID, and we can choose any country. So if you want me to run this code for your country, I can just choose your country here, and it will do the same. It will basically do the same thing. And then what is important also is that this data is updated automatically because it's here in this GitHub here. So it delays by just maybe 1 day or something like that. So it means this code, I ran it yesterday before I left the office. So the data that I ran is very, it's for yesterday or for 2 days ago and stuff like that. And this is for South Africa. So the code that I'm showing you is for South Africa. So here, what we do, we just choose data for South Africa and just we plot it, and we denoise it a bit using wavelet denoising just to remove a bit of noise in it. And we plot both the not denoised and denoised data in here. So you can see that if you are a time series person, you can see that these waves are increasing. And this was the strongest, but this was the broadest and stuff like that. So if you plot the trend of this, it will probably be outwards. This was very bad actually, because I didn't, even this corona here, even myself, it got me. And this one, it may have got me, but I don't know what, I didn't feel sick. So then we took this time series, we say, okay, let's take this time series, divide it into 70-30 and push it into these structures here. And I should say that we also need CHPC computer here. We had to decompose our module so that it doesn't run everything at the same time, because we get stuck. So now that I have this relationship with CHPC, I'm hoping to run all these models inside CHPC so that our job is really easy. So different models then will have different functions that are now in our.
Sorry, Dr. Mbatha. There is a question in the chat. What is the meaning of IMF?
It's an intrinsic mode function. When you decompose, you are like creating a filter bank where you filter maybe like think about something like a high pass filter, where you just have a high pass filter that keeps on shifting and shifting and shifting and shifting. Meaning, if I decompose and take maybe one IMF, then that IMF will be a sort of a representation of filtered data. You'll find out that maybe the high pass part was removed or something like that. So intrinsic mode functions are like that. But when you use empirical wavelet transform, it's a bit of a different method. The reason why I wrote the paper that I wrote to compare this and this was because this has no good mathematical theory, but here we're using Fourier analysis in wavelets and stuff like that to get these different values. So filtered data will look like something like, decomposed data will look like something like this. So let me say EMD decomposed. So if you look at images, it's something like this. You have, for instance, original time series that you decompose into different intrinsic mode functions like this. If you add these intrinsic mode functions, they give you the same main time series that you decompose. So it's something like that.
Okay.
And then
I hope that's answering the question of Martin, who's asked this question in the chat.
Okay. So that's what happened here. So it means you can take this, you can thereafter run these models. These models are different. One could be a straight model, and we are able to switch on or switch off denoising and decomposing. For instance, if I don't want to decompose and denoise, I'll say false, and then it will just run an LSTM on the data. And so on. And I can define how many apples you saw, what apples do in your data, and you can just define how many apples you want them to write. You can feed your data, your window size and stuff like batch size, all these inputs of an LSTM, if you have seen LSTM, and you can just plot train validation loss, square error, something like that. see it stabilizes at around this point here for both training and validation. So we do that, we play around with that a lot also so that we understand our model perform and stuff like that. For instance, here we did 10 apples because if we do more apples, then we need to wait here, of course, because as I said, we don't have a supercomputer here. So you need to improvise, maybe run a few apples and stuff like that. But the better thing is to run about 100 apples and so on. So for the final work, we run 100 apples. The main module that we created, or the main package that we created, which is currently not published, of course, meaning you cannot use it. But if you want to use it, of course, you can talk to me if you want to do some forecasting. The main thing is that, it's one code and you can choose which model, which decomposing method you want to use so that it can direct you to the type of model that you want to do. For instance, we have what is called EEMD, which means it used empirical mode decomposition. We also have wavelet denoised EEMD, wavelet denoised EEMD. It means you denoise the data because before you decompose it using EMD and then push it into an LSTM. So we have all these models running. So this is all the training and validation plots that we did. I just wanted to go towards the end before our time ends so that we have time for questions and chatting. So for instance, this is the last model that we ran. We were using empirical wavelet transform to decompose, and we didn't want to denoise, we just wanted to decompose. Okay, so this is the stats, the outputs, how the model performs. We just compare all the models in terms of your root mean square error, your mean square error, your directional symmetry, for instance. You will notice that always this the model that uses empirical wavelet transform normally will perform better than the others and stuff like that. So that's what we noted, and we do plot that. For instance, these are model performances for Egypt. You'll see that if you do not denoise, and you just take the data and push it into an LSTM, it performs very well here. What we notice is that if you denoise the data, because this is a short-term neural network, it learns short-term and also something that happened long-term in the time series. It is able to see if you have removed some of the short-term variabilities through wavelet denoising. Hence, it does not perform as well as just pushing the data into the wavelet, the empirical wavelet transform and LSTM. So that's what we did. Well, we decided to do what is called directional symmetry as well. This is directional symmetry because we think that if the test part, so all this test statistics is done on the test part of the time series. The other is just a training part where we train our model. So the test part of the time series, when we introduce this directional symmetry, you can see here also it performs very well for the data that is not denoised. It goes all the way to above 95 and so on. And directional symmetry, because we think that this could be a very good additional statistic, because what you do is if both the test and the forecasted time series are positive, then that is positive. If this one is positive and this one is negative, then that is negative and so on. And then when you count all those episodes where if you look at each and every point on the time series, you will see that directionally the two are symmetric and stuff like that. Then you can calculate that the relationship between the two is good. So that's that, and that's what we are doing here. So we do have this small project that we are doing where we are applying this in different things. Our idea is to apply this on rainfall and finance data and all those things. We have done that before because it started from applying it on ozone for atmospheric science. So we wrote this nice paper with my professor from France, where we use LSTM to forecast the ozone in the atmosphere. And also we use LSTM and empirical wavelet transform to, so we created this model this way, and we forecasted the time series of ozone this way, and we decomposed it using empirical mode decomposition and empirical wavelet transform. And we also were able to find a new method of extracting a trend using empirical wavelet transform, because this has very good mathematical theory compared to this one. And then we checked our model performance and stuff like that, and we discovered that the empirical wavelet transform improved the model greatly. So, and then after that, now we had to do improved methods on the decomposition of the time series, on how you can forecast a time series and stuff like that. So we have that if you are interested, maybe because we are not working with anyone, it's just me and my PhD student, but I know that there are many people who are doing machine learning and stuff like that, who can work with us. Okay, so I think we can stop here, maybe chat about questions.
Okay. I don't see any questions.
Do you have any questions, or maybe where I can clarify something like that?
Yes, somebody is asking whether they can get access to the notebooks.
Okay, this, I think we can talk to me, we can talk about that, because we have, this notebook has a package that we created, and this package, we wanted to publish this paper before we let everyone to use our package or something like that, let me say it like that. But if you want to use it, of course, you can work with me, and whatever you are doing, we can work together and stuff like that. So we can talk about if you want to use the package or not, and you can use it.
Okay, Dr. Mbatha, maybe you can put in the chat your email address so that Malelo can contact you, and you can make kind of a connection, and you can maybe start working together.
Okay, so this is my email. Okay. Is there any other question or comment or something like that?
Okay.
Okay, so no problem, but well, if you think two things, if you think you want to use X-rays and Catopy in whatever visualization you are doing, you can speak to me. By the way, some of you would like to do empirical orthogonal functions on your spatial data. You can also do that much more easier with empirical wavelet transform, even maximum covariance and all those things. You can do it much more easier inside the X-ray. With regards to this, of course, you can talk to me if you are.
Okay. And there is a question in the chat also. Is it possible to try this on Neo4j? But I'm not sure what is the Neo4j.
Well, I don't know too. I don't know this. Another thing is that, I know that I'm talking about LSTM here as my deep learning model that I use. Our model is free to change from LSTM to NBIDS or some time series based convolution neural networks like TCNs. I'm sure you have seen some TCNs if you are doing neuro time series forecasting using neural networks. We can do that also. So the code itself it just needs someone who want to do it, of course, because I'm also doing something else. Maybe the PhD student is also concentrating on this. I do not know what is Neo4j. I'm very sorry. Maybe if you can tell us.
Judin, if you can unmute yourself and maybe yes, tell us what is the Neo4j, that would be great. Okay, so there is one more question, and I think this one is a little bit more generic.
Well, yeah, this, let me tell you something, some signals which are very easily predictable, the model performs very well. But like in this corona, the model performs very well, let me tell you. But what I've noticed is that when I use it on Mercury, there is Geosciences at Cape Point where they take data from Mercury. So they have very good record on Mercury. And also my friend from Germany gave me Mercury data from there to apply on this. I need to have a very long time series for the model to learn more of the time series for it to perform better, because Mercury does not depend, is not seasonal, you know, you just, you know, it may depend on the days, wind, direction, I don't know. I have not studied Mercury to see what exactly, how it varies, but it's a very fun signal. Sometimes in the Northern Hemisphere, it has a downward trend. Here we have an upward trend and stuff. So the performance of the model, you know, that's where you see that, yeah, you need a bigger time series. So the German time series was very long, so the model could learn this time series. But the Cape Point time series was a bit short. That's where you see that the capabilities of the model. And then another thing about the performance of these models is that in the same code that we are using, so that we test the model capabilities, it is not to have a static system where we're saying 70%, 30%, 70% training and 30% testing. We want to start maybe from 50% and keep on shifting maybe by 5% the time series, so that we have a statistic of the performance of the model to predict the testing part of the model. If you play around with these models, you'll see that they are capable up to this far and so on.
Okay. Thank you.
I hope that's fine.
I also hope so. Yes, I don't see any more questions. So what I need to do, I need to thank not only Dr. Mbatha, but also all the speakers of this course on the Earth climate and climate change and Earth weather modeling. And thank you very much. And we will see the students tomorrow, the last day of the summer school, where we're still having talks on bioacoustics, machine learning for bioacoustics, and if I'm not mistaken, the introduction to R. Thank you very much. Thank you, Dr. Mbatha, for your nice talk. Thank you. Bye-bye.
Thank you.